Have you ever wondered what ancient Colorado looked like when massive predators stalked humid swamplands and armored giants roamed vast floodplains? Well, during the Cretaceous period, this region was nothing like the mountainous landscape we know today. Instead, it was a prehistoric paradise teeming with some of the most incredible dinosaurs ever discovered. What I'm about to show you will completely change how you picture ancient America. We're talking about a time when Colorado sat beneath shallow seas, when rivers meandered through lush deltas, and when creatures that would make today's largest animals look like house pets ruled the land. This isn't just another dinosaur documentary. This is Colorado Cretaceous madness. And by the end of this series, you'll understand why paleontologists consider this region one of the most important fossil sites in North America. But first, let me paint you a picture of just how wild this really gets. Imagine walking through what is now Colorado and encountering a 20-foot-long armored tank of a dinosaur covered in bony spikes and plates. Picture massive duck-billed herbivores with crests that could produce haunting musical calls echoing across prehistoric wetlands. Envision razor-clawed predators with sickle-shaped talons designed for precision killing. This was Colorado during the Cretaceous, and the fossil evidence we've uncovered tells an absolutely incredible story. The geological formations we'll be exploring today represent millions of years of ancient history preserved in stone. These rock layers didn't just randomly appear. They were formed by specific environmental conditions that created perfect fossilization scenarios. Rivers carried sediments from ancient mountain ranges, depositing them across sprawling floodplains. When these rivers periodically flooded, they buried countless animals in muddy graves that would eventually become their eternal resting places. What makes Colorado's Cretaceous deposits so special is the incredible diversity of environments they represent. We're not just looking at one type of ecosystem. These formations show us evidence of braided rivers, meandering channels, lake shores, and even coastal plains. Each environment supported different communities of dinosaurs, creating a complex web of prehistoric life that scientists are still working to fully understand. Let's start our journey with one of the most remarkable armored dinosaurs ever discovered in these deposits. This creature was essentially a living fortress, covered from head to tail in protective bony armor. Its back was adorned with rows of spikes and plates that would have made any predator think twice before attacking. But here's what's really fascinating about this particular dinosaur. Despite its intimidating appearance, it was completely herbivorous, spending its days peacefully browsing on low-growing vegetation. The defensive capabilities of this armored giant were truly extraordinary. The bone plating wasn't just for show. Each piece was strategically positioned to protect vital organs and create an almost impenetrable shield. The tail was particularly impressive, ending in a massive club of fused bone that could deliver devastating blows to any attacker foolish enough to get too close. Recent studies have shown that the muscle attachments for this tail club were incredibly robust, suggesting these dinosaurs could swing their tails with tremendous force. But defense wasn't the only consideration for these armored herbivores. They also had to be efficient eating machines to fuel their massive bodies. Their skulls were perfectly adapted for processing tough plant material, with specialized teeth designed for grinding rather than slicing. The jaw muscles were positioned to maximize the force applied during chewing, allowing them to break down even the most fibrous vegetation. Living alongside these armored tanks were some of the most abundant herbivorous dinosaurs of the Cretaceous period. These were the marathon runners of the dinosaur world, built for speed and endurance rather than defense. Their long, powerful legs could carry them across the floodplains at impressive speeds, helping them escape from the numerous predators that shared their environment. What's particularly interesting about these swift herbivores is their social behavior. Fossil evidence suggests they may have lived in groups, possibly even large herds that moved together across the landscape. This would have provided additional protection through the simple principle of safety in numbers. When predators approached, the entire group could scatter in different directions, making it difficult for any single individual to be targeted. The anatomy of these running dinosaurs reveals incredible adaptations for their lifestyle. Their leg bones show proportions that are remarkably similar to modern fast-running animals. The lower leg bones were significantly longer than the upper leg bones, a feature that increases stride length and running efficiency. Their feet were equipped with sharp claws that would have provided excellent traction on various surfaces, from muddy riverbanks to harder ground. But perhaps the most distinctive feature of these herbivores was their incredibly long tails. These weren't just decorative appendages. They served as dynamic counterbalances during high-speed running and quick directional changes. The tail was supported by an intricate network of ossified tendons that kept it rigid and perfectly positioned for optimal balance. This adaptation was so effective that the tail actually comprised more than half of the animal's total body length. Now, where there are herbivorous dinosaurs, there are inevitably predators to hunt them, and the Cretaceous formations of Colorado have yielded some of the most fearsome carnivorous dinosaurs ever discovered. These weren't just large predators. They were sophisticated killing machines with adaptations that would make modern apex predators seem primitive by comparison. One of the most distinctive features of these Cretaceous predators was their incredible sensory capabilities. Recent studies of their brain cases have revealed enlarged olfactory regions, indicating an exceptional sense of smell that would have allowed them to track prey across vast distances. Their eye sockets show adaptations for binocular vision, giving them the depth perception necessary for precision strikes during attacks. But it's their weaponry that truly sets these predators apart. While many people focus on their impressive teeth, it was actually their feet that were their most deadly feature. Each foot was equipped with a large sickle-shaped claw on the second toe that could be rotated through a wide arc. This wasn't a slashing weapon as many people assume. Instead, it was designed for precise stabbing attacks aimed at vital areas like the neck or major blood vessels. The forelimbs of these predators were equally impressive, though often overlooked. They were perfectly positioned for grappling with prey, allowing the predator to maintain control while delivering fatal wounds with their foot claws. The muscle attachments on these arm bones show evidence of tremendous strength, capable of holding on to even large, struggling prey animals. These predatory dinosaurs also show evidence of pack hunting behavior, which would have made them even more formidable. Multiple skeletons are often found in association with the remains of large herbivorous dinosaurs, suggesting coordinated attacks on prey much larger than any individual predator could handle alone. This level of social cooperation among predators represents a sophisticated behavioral adaptation that increased their hunting success dramatically. The diversity of predatory dinosaurs in these formations is truly remarkable. Alongside the sickle-clawed hunters were massive carnivores with distinctive high spines running along their backs. These giants were among the largest predators of their time, with skull proportions that indicate incredibly powerful bite forces. Their spinal adaptations likely supported massive muscle attachments, giving them the strength needed to take down the largest herbivorous dinosaurs of their era. But the Cretaceous ecosystems of Colorado weren't just dominated by dinosaurs. The formations also preserve evidence of other remarkable reptiles, including freshwater turtles with specialized feeding adaptations. These aquatic reptiles had evolved unique skull features that suggest they were suction feeders, using rapid expansion of their throat cavity to draw in prey and water simultaneously. The environmental conditions that supported this incredible diversity of life were quite different from modern Colorado. The climate was much warmer and more humid, with no ice caps at the poles and sea levels significantly higher than today. Flowering plants were just beginning to diversify, though they hadn't yet become the dominant vegetation we see in modern ecosystems. Instead, the landscape was dominated by ferns, cycads, and coniferous trees. These plants formed the base of complex food webs that supported multiple levels of herbivorous and carnivorous dinosaurs. The herbivores had to develop specialized feeding strategies to process these tough, fibrous plants, leading to the evolution of sophisticated tooth batteries and powerful jaw muscles. The river systems that created these fossil-rich formations were dynamic environments, constantly changing course and flooding surrounding areas. These periodic floods were actually crucial for fossil preservation, rapidly burying animals and plants before decomposition could destroy them completely. The sediments carried by these ancient rivers came from mountain ranges that were actively forming to the west, providing a constant supply of material for fossil preservation. What we're seeing in these Colorado formations represents just a snapshot of Cretaceous life, but it's an incredibly detailed snapshot that reveals the complexity and diversity of these ancient ecosystems, the interactions between predators and prey, the adaptations for different feeding strategies, and the evidence of social behaviors all paint a picture of a vibrant prehistoric world that was every bit as complex as modern ecosystems. The story we're uncovering from these rocks challenges many of our preconceptions about dinosaur behavior and ecology. These weren't simple, primitive animals stumbling through a harsh prehistoric world. They were sophisticated creatures with complex behaviors, specialized adaptations, and intricate ecological relationships that allowed entire communities to thrive for millions of years. As we dig deeper into these ancient Colorado ecosystems, we encounter some truly bizarre creatures that challenge everything we thought we knew about dinosaur diversity. Take, for instance, the small theropods that roamed these prehistoric landscapes. These weren't your typical razor-toothed predators. Instead, they represent some of the most enigmatic dinosaurs ever discovered, with feeding habits that continue to puzzle paleontologists today. One particularly fascinating group of these smaller dinosaurs had developed an almost bird-like appearance, complete with long legs built for rapid movement across the varied terrain. Their skulls reveal something extraordinary. Rather than the typical predatory teeth we'd expect from theropods, these creatures had developed specialized dental arrangements that suggest a completely different lifestyle. Some possessed simple, pointed teeth in the front of their jaws, while the back teeth were more complex and designed for processing different types of food. This dental specialization tells us something remarkable about the flexibility of dinosaur evolution. These creatures weren't locked into a single feeding strategy like many of their relatives. Instead, they could adapt their diet based on seasonal availability of resources, switching between different food sources as needed. During certain times of the year, they might have focused on small animals, insects, or eggs. At other times, they could have supplemented their diet with seeds, fruits, or other plant materials. The postcranial skeleton of these adaptable dinosaurs reveals equally interesting features. Their limb proportions suggest they were capable of both swift running and more precise movements needed for foraging. The length ratio between their lower and upper leg bones indicates exceptional running ability, while their hand structure shows adaptations for grasping and manipulating objects with considerable dexterity. But perhaps the most intriguing aspect of these creatures is their potential relationship to later dinosaur groups. Some specimens show primitive characteristics that place them at crucial evolutionary junctions, representing early experiments in dinosaur body plans that would later give rise to more specialized forms. These transitional fossils provide invaluable insights into how major dinosaur groups evolved and diversified throughout the Cretaceous period. Moving from these enigmatic small theropods, we encounter another group of dinosaurs that represents a completely different evolutionary approach to herbivory. These were the dome-headed dinosaurs, creatures whose skulls underwent one of the most extreme modifications seen in any vertebrate group. The bone thickening on top of their skulls could reach incredible dimensions, creating massive domed structures that have fascinated scientists for decades. The function of these remarkable skull domes has been debated extensively, with theories ranging from headbutting combat to display structures used in social interactions. Recent research suggests the reality was probably more complex than either extreme. The bone structure shows evidence of being able to withstand significant impact forces, but the arrangement of muscle attachments and the overall skull architecture indicate these weren't simple battering rams. Instead, these dome-headed dinosaurs likely used their reinforced skulls in a variety of social contexts. During territorial disputes, they might have engaged in head-pushing contests similar to those seen in modern bighorn sheep. The visual impact of these massive skull domes would have been equally important for species recognition and courtship displays, allowing individuals to assess the health and maturity of potential mates or rivals. The body structure of these dinosaurs reveals additional adaptations for their unique lifestyle. Their necks were reinforced with additional bone structures to handle the stresses generated by their heavy skulls. The vertebral column shows modifications that distributed weight more effectively, preventing injury during the various head-based behaviors these creatures likely engaged in. What makes these dome-headed dinosaurs particularly interesting is their dental adaptations. Unlike many other herbivorous dinosaurs that developed elaborate tooth batteries for processing tough plant material, these creatures retained relatively simple teeth with sharp serrated edges. This suggests they focused on softer plant materials, possibly including fruits, seeds, and young shoots that didn't require extensive processing before swallowing. The diversity of plant-eating strategies during the Cretaceous period was truly remarkable, and nowhere is this more evident than in the duck-billed dinosaurs that inhabited these ancient Colorado landscapes. These creatures represent perhaps the pinnacle of herbivorous dinosaur evolution, with some of the most sophisticated feeding mechanisms ever developed by any land animal. The dental batteries of these duck-billed giants contained hundreds of individual teeth arranged in complex interlocking patterns. As teeth wore down from constant use, new ones continuously emerged to replace them, creating a self-sharpening cutting surface that could process even the toughest vegetation. This system was so efficient that it allowed these dinosaurs to exploit food sources that were unavailable to other herbivores. But the feeding adaptations of duck-billed dinosaurs extended far beyond their impressive teeth. Their broad, flattened beaks were perfectly designed for different feeding strategies. Some species could crop vegetation like modern geese, while others could strip nutritious leaves and shoots from branches using a clamshell-like jaw motion that maximized the amount of food gathered with each bite. The digestive systems of these herbivorous giants were equally impressive. Their massive gut capacity allowed them to maintain large populations of symbiotic bacteria that could break down cellulose and other complex plant compounds that would be indigestible to most animals. This internal fermentation process was so effective that it could extract nutrients from even low-quality vegetation, allowing these dinosaurs to thrive in environments where other herbivores might struggle. Evidence from bone bed discoveries suggests that many of these duck-billed dinosaurs were highly social animals, living in large herds that moved across the landscape together. These mass gatherings would have provided numerous advantages, from improved predator detection to enhanced foraging efficiency through cooperative feeding behaviors. The most distinctive feature of many duck-billed dinosaurs, however, was their elaborate head crests. These weren't just decorative structures. They housed complex internal air passages that could produce a wide range of sounds, essentially turning each dinosaur's skull into a sophisticated musical instrument. Different species had different crest shapes and sizes, which would have produced unique acoustic signatures that allowed for species recognition across vast distances. Recent computer modeling of these crest structures has revealed the incredible range of sounds these dinosaurs could produce, from deep, resonant calls that could travel for miles across open floodplains to higher-pitched vocalizations used for close-range communication within herds. These creatures had developed one of the most advanced acoustic communication systems in the animal kingdom. The social implications of this acoustic capability were enormous. Herds could maintain contact even when spread across large areas, coordinate movement patterns, and warn of approaching dangers. Parents could maintain contact with their young in dense vegetation, and individuals could establish and maintain their position within complex social hierarchies through vocal displays. As we examine the predator-prey relationships in these ancient ecosystems, we begin to see patterns of evolutionary arms races that played out over millions of years. The development of increasingly sophisticated defense mechanisms in herbivorous dinosaurs was matched by equally impressive adaptations in their predators. This constant pressure for improvement drove both groups to evolutionary heights that seem almost impossible by today's standards. The largest predators of these Cretaceous ecosystems were truly magnificent creatures, combining massive size with surprising agility and intelligence. Their brain structure reveals enlarged regions associated with sensory processing, particularly areas related to vision and spatial awareness. This neural architecture suggests these predators were capable of complex hunting strategies and sophisticated prey assessment. The killing methods employed by these apex predators were far more refined than the simple slashing attacks often portrayed in popular media. Their primary weapons were precision instruments designed for specific types of damage. The famous sickle claws were positioned and shaped to deliver targeted stabbing attacks to critical areas, while their powerful forelimbs provided the control necessary to maintain contact with struggling prey. Evidence suggests these large predators may have employed different hunting strategies depending on the size and type of prey they encountered. When hunting smaller, faster herbivores, they likely relied on ambush tactics, using their exceptional sensory capabilities to detect and track prey before launching devastating surprise attacks. Against larger herbivores, they may have employed persistence hunting, using their endurance and intelligence to wear down prey over extended periods. The diversity of predatory strategies extended to the medium-sized carnivores as well. These creatures occupied a unique ecological niche, being too large to rely primarily on small prey, but not large enough to regularly take down the massive herbivores that dominated the landscape. Instead, they likely specialized in hunting juvenile dinosaurs, exploiting the vulnerable period between hatching and reaching adult size. This focus on juvenile prey would have required different adaptations than those seen in the apex predators. Speed and agility would have been more important than raw power, leading to the evolution of highly cursorial body plans optimized for pursuit hunting. Their sensory capabilities would have been tuned to detect the specific behavioral patterns and vocalizations of young dinosaurs, allowing them to locate and target the most vulnerable individuals. The impact of predation pressure on herbivorous dinosaur evolution cannot be overstated. Every aspect of their anatomy, behavior, and life history was shaped by the constant threat of predation. This pressure drove the evolution of increasingly sophisticated defense mechanisms, from the massive body armor of ankylosaurs to the complex social behaviors of duck-billed dinosaurs. But predation pressure also influenced more subtle aspects of herbivore biology. Growth rates, reproductive strategies, and even dietary choices were all affected by the need to minimize vulnerability to predators. Fast growth rates allowed young dinosaurs to reach safer adult sizes more quickly, while specific dietary preferences might have developed to avoid areas where predators were most likely to hunt. The seasonal patterns preserved in these geological formations reveal additional layers of complexity in these ancient ecosystems. Periodic flooding events created temporary changes in habitat availability, forcing both predators and prey to adapt their behaviors accordingly. During flood seasons, many animals would have been concentrated on higher ground, creating intense competition for resources and increased predation pressure. These environmental fluctuations also created opportunities for different species to exploit temporary ecological niches. Some dinosaurs may have been specialized for taking advantage of post-flood conditions, when decomposing organic matter created ideal feeding opportunities for certain types of herbivores and the insects that fed on them. The preservation of these complex ecological relationships in the fossil record provides us with an unprecedented window into the functioning of Cretaceous ecosystems. We can see not just individual species, but entire communities of organisms interacting in ways that created stable, productive environments that persisted for millions of years. What emerges from this detailed examination is a picture of prehistoric Colorado as a dynamic, complex ecosystem where every species was connected to every other species through intricate webs of interaction. The loss of any single species would have had cascading effects throughout the entire system. Yet these communities showed remarkable resilience in the face of environmental changes. This resilience was built on the incredible diversity of ecological strategies that had evolved among Colorado's Cretaceous dinosaurs. From the heavily armored herbivores that could survive almost any predator attack to the swift runners that relied on speed and alertness, from the sophisticated pack hunters to the massive apex predators, each species had carved out its own unique role in these ancient ecosystems. The story of Cretaceous Colorado is ultimately a story of evolutionary success on a scale that's difficult to comprehend. For tens of millions of years, these diverse communities of dinosaurs thrived in environments that supported levels of biomass and diversity that rival anything seen in the modern world. Understanding how these systems worked provides crucial insights into the fundamental principles of ecology and evolution that continue to shape life on Earth today. The feeding strategies of these ancient Colorado herbivores reveal adaptations that seem almost alien compared to modern plant eaters. Consider the ceratopsian dinosaurs that roamed these prehistoric landscapes. These weren't just rhinoceros-like creatures with impressive horns and frills. They were living embodiments of evolutionary engineering, with skulls that functioned as sophisticated food processing plants. The massive heads of these horned dinosaurs served multiple functions beyond simple intimidation displays. Their powerful jaw muscles were arranged in configurations that maximized bite force, allowing them to shear through the toughest vegetation available during the Cretaceous period. The sharp, beak-like structure at the front of their mouths worked like precision pruning shears, capable of severing branches and stripping away bark with remarkable efficiency. Behind this cutting apparatus lay batteries of specialized teeth that worked together in a continuous grinding motion. As vegetation entered their mouths, it was systematically broken down by rows of interlocking dental elements that created a self-maintaining cutting surface. Worn teeth were continuously replaced by fresh ones emerging from below, ensuring that these feeding machines never lost their efficiency. The neck frills that make these dinosaurs so visually striking weren't merely decorative features or simple defensive shields. Recent analysis of muscle attachment sites suggests these structures supported incredibly powerful neck muscles that allowed for complex head movements during feeding. These dinosaurs could manipulate their massive skulls with surprising precision, positioning their cutting tools at optimal angles to process different types of vegetation. What's particularly fascinating about these horned giants is their apparent specialization for different plant communities. Variations in skull proportions and dental arrangements between species suggest they had partitioned the available food resources, with some focusing on tougher, more fibrous vegetation, while others specialized in processing softer plant materials. This resource partitioning allowed multiple species to coexist in the same environments without direct competition for food. The social dynamics of these ceratopsian herds would have been incredibly complex. Evidence suggests they lived in large groups that moved across the landscape in coordinated patterns, following seasonal changes in plant availability. The massive bone beds discovered in Colorado formations indicate that hundreds or even thousands of individuals sometimes gathered together, creating prehistoric assemblages that would have dominated entire landscapes. But these peaceful giants faced constant threats from some of the most formidable predators ever to evolve. The apex carnivores of Cretaceous Colorado had developed hunting strategies that seem almost too sophisticated for creatures that lived over 100 million years ago. Their approach to predation involved careful assessment of potential prey, strategic positioning, and coordinated attacks that maximize success rates while minimizing energy expenditure. The sensory capabilities of these top predators were extraordinary by any standard. Their brain structure reveals enlarged regions devoted to processing visual information, with specialized areas that would have allowed them to track moving objects across vast distances. The positioning of their eyes provided overlapping fields of view that created exceptional depth perception, essential for judging distances during high-speed pursuits. Their olfactory capabilities were equally impressive. The enlarged nasal passages and associated brain regions indicate these predators could detect scent trails hours or even days old, allowing them to track prey across the complex terrain of ancient Colorado. This chemical sensing ability would have been particularly valuable during the dry seasons when prey animals concentrated around limited water sources. The hunting techniques employed by these predators varied depending on the target species and environmental conditions. When stalking the swift ornithopod dinosaurs that inhabited open floodplains, they likely relied on ambush tactics, using natural cover to approach undetected before launching explosive attacks. Their powerful leg muscles were perfectly adapted for these sudden bursts of speed that could close distances in seconds. Against larger, more heavily defended prey, these predators employed different strategies entirely. Rather than relying on surprise attacks, they used persistence and intelligence to wear down their targets over extended periods. Their cardiovascular systems were adapted for sustained activity, allowing them to maintain pursuit over long distances until their prey became exhausted and vulnerable. The weapon systems of these apex predators were marvels of biological engineering. While their impressive teeth certainly played a role in killing and processing prey, it was their specialized foot claws that served as their primary weapons. These weren't crude slashing implements, but precision stabbing tools designed to penetrate vital organs and major blood vessels with surgical accuracy. The mechanics of how these claws were employed reveals the sophistication of these predators' attack strategies. Rather than simply raking across their prey's body, they used their powerful leg muscles to drive these weapons deep into critical anatomical targets. The curved shape and reinforced structure of these claws ensured they could penetrate even thick skin and dense muscle tissue to reach vital organs beneath. The forelimbs of these predators served an equally important function in their hunting arsenal. While often portrayed as vestigial appendages, these arms were actually powerful grappling tools that allowed predators to maintain control over struggling prey. The muscle attachment sites on these bones indicate tremendous gripping strength, sufficient to hold on to animals many times the predator's own weight. This combination of grappling arms and stabbing foot claws created a hunting system of devastating effectiveness. Predators could seize their prey with their forelimbs, preventing escape, while simultaneously delivering fatal wounds with their hind feet. The coordination required for this type of attack suggests these creatures possessed sophisticated motor control systems that rival those of modern predators. The social hunting behaviors exhibited by some of these Cretaceous predators adds another layer of complexity to their already impressive capabilities. Evidence from multiple fossil sites suggests that certain species engaged in coordinated pack hunting, with different individuals playing specialized roles during attacks on large prey animals. These cooperative hunting strategies would have allowed relatively small predators to take down herbivores many times their individual size. By working together, they could surround and isolate target animals, preventing escape while multiple pack members delivered simultaneous attacks. The level of communication and coordination required for such hunting methods indicates cognitive abilities that challenge our understanding of dinosaur intelligence. The impact of these predation pressures on herbivorous dinosaur evolution created an arms race that drove innovation on both sides. As predators became more efficient hunters, prey species developed increasingly sophisticated defense mechanisms. This evolutionary pressure resulted in some of the most remarkable adaptations seen in any ecosystem, past or present. The armored dinosaurs represent perhaps the ultimate expression of defensive evolution. Their body armor wasn't simply a collection of random bony plates, but a carefully engineered defensive system that provided protection while maintaining mobility. Different species developed distinct armor configurations optimized for defending against specific types of predator attacks. Some armored dinosaurs focused on creating impenetrable back protection, with overlapping plates that could deflect even the most powerful predator claws. Others developed specialized tail weapons that could deliver devastating counterattacks to any predator bold enough to approach from behind. The variety of defensive strategies employed by these creatures demonstrates the diverse selection pressures they faced from different predator species. The smaller, more agile herbivores pursued completely different defensive strategies based on speed and alertness rather than armor. Their sensory systems were tuned for maximum sensitivity to predator presence, with large eyes positioned to provide panoramic vision and enlarged ear structures for detecting the slightest sounds that might indicate approaching danger. These swift herbivores also developed sophisticated group coordination behaviors that enhanced their survival chances. Herding provided multiple sets of eyes and ears to detect threats, while coordinated movement patterns made it difficult for predators to single out individual targets. The ability to rapidly change direction and speed during escape attempts created additional challenges for pursuing predators. The seasonal migration patterns of these herbivorous herds created dynamic changes in the distribution of both prey and predators across the landscape. During certain times of the year, vast numbers of plant eaters would concentrate in specific areas, creating temporary abundance that attracted predators from across the region. These seasonal gatherings would have been times of intense predation pressure, but also opportunities for social interactions and reproduction. The reproductive strategies of Cretaceous dinosaurs were intimately connected to these predation pressures. Many species developed rapid growth rates that allowed their focus on producing large numbers of offspring to reach safer adult sizes as quickly as possible. Others to ensure that some would survive despite heavy predation on juveniles. Nesting behaviors also reflected the constant threat of predation. Some species built elaborate nests in hidden locations, while others relied on communal nesting areas where multiple adults could cooperate in defending their young. The diversity of reproductive strategies employed by different species created complex breeding cycles that affected the entire ecosystem's dynamics. The environmental conditions that supported these complex predator-prey relationships were maintained by the dynamic geological processes that shaped Cretaceous Colorado. The constant deposition of sediments from eroding mountain ranges created new habitats, while burying others, ensuring that the landscape remained in a state of continuous change that promoted evolutionary innovation. River systems meandered across vast floodplains, creating a mosaic of different habitat types that supported specialized communities of dinosaurs. Oxbow lakes provided breeding grounds for aquatic species, while elevated terraces offered nesting sites for terrestrial forms. This habitat diversity was crucial for maintaining the high levels of species richness that characterized these ancient ecosystems. The climate during this period was remarkably stable compared to more recent geological times, with consistently warm temperatures and high humidity levels that supported lush vegetation growth throughout the year. This climatic stability allowed complex ecological relationships to develop and persist over millions of years, creating the intricate food webs that we're only now beginning to understand. The plant communities that formed the base of these food webs were undergoing their own evolutionary revolution during the Cretaceous period. While flowering plants were beginning to diversify, the landscape was still dominated by more ancient plant groups including ferns, cycads, and various types of conifers. Each of these plant groups had different nutritional profiles and defensive chemicals that influenced which herbivorous dinosaurs could effectively exploit them. The coevolution between plants and their dinosaurian herbivores created feedback loops that drove innovation in both groups. As plants developed new defensive compounds or physical barriers to prevent consumption, herbivores evolved counter-adaptations that allowed them to overcome these defenses. This ongoing evolutionary arms race contributed to the incredible diversity of feeding strategies we observe in Cretaceous herbivorous dinosaurs. The preservation of these complex ecological relationships in Colorado's fossil record provides us with unparalleled insights into how ancient ecosystems functioned. We can trace the flow of energy from primary producers through multiple levels of consumers, revealing the intricate connections that maintained these prehistoric communities for tens of millions of years. What emerges from this detailed analysis is a picture of Cretaceous Colorado as one of the most productive and diverse ecosystems in Earth's history. The combination of favorable climate, dynamic geology, and evolutionary innovation created conditions that supported biomass levels and species diversity that exceeded anything seen in modern terrestrial environments. The legacy of these ancient ecosystems extends far beyond their immediate participants. The evolutionary innovations developed by Cretaceous dinosaurs influenced the trajectory of vertebrate evolution for millions of years afterward. Many of the basic body plans and ecological strategies that first appeared during this period continue to influence animal design even today. Understanding these prehistoric ecosystems also provides crucial insights into how modern environments might respond to current environmental changes. The resilience and adaptability demonstrated by Cretaceous communities offer both hope and warnings about the future of biodiversity on our rapidly changing planet. The story of Colorado's Cretaceous madness is ultimately a testament to life's incredible capacity for innovation and adaptation. In the face of constant challenges from predation, competition, and environmental change, these ancient creatures developed solutions that pushed the boundaries of what seemed biologically possible. Their legacy continues to inspire and inform our understanding of evolution, ecology, and the fundamental processes that shape life on Earth. The aquatic environments within these Cretaceous Colorado ecosystems supported their own remarkable communities of specialized reptiles. Freshwater turtles had evolved extraordinary feeding mechanisms that set them apart from their modern relatives. These ancient chelonians developed skulls with unique adaptations that transformed them into highly efficient underwater hunters. The suction feeding capabilities of these prehistoric turtles represented a fascinating evolutionary solution to aquatic predation. By rapidly expanding their throat cavities, they could create powerful vacuum forces that drew prey and water into their mouths simultaneously. This feeding strategy allowed them to capture fast-moving fish and aquatic invertebrates with remarkable precision, even in murky water where vision was limited. The skull modifications required for this feeding method were extensive. The jaw structure had to be reinforced to withstand the pressures generated during suction events, while maintaining the flexibility needed for rapid expansion and contraction. The positioning of muscle attachments shows these creatures could generate tremendous suction forces while maintaining fine control over the process. These aquatic predators occupied ecological niches that were completely unavailable to terrestrial dinosaurs, creating additional layers of complexity within the overall ecosystem structure. Their presence in rivers and lakes provided checks and balances that influenced the behavior patterns of other animals that came to drink or feed near water sources. The diversity of turtle species during this period suggests that aquatic habitats were highly productive and supported multiple specialized feeding strategies. Some species likely focused on bottom-dwelling invertebrates, while others may have specialized in capturing surface-dwelling prey or even scavenging from carcasses that washed into the water systems. Moving beyond the aquatic realm, we encounter some of the most enigmatic creatures in the entire Cretaceous fossil record. Small theropod dinosaurs with feeding adaptations that continue to puzzle researchers represent some of the most significant evolutionary experiments of this time period. These creatures challenge our traditional understanding of predatory dinosaur ecology. The dental arrangements found in these mysterious theropods suggest feeding strategies that were remarkably flexible and opportunistic. Rather than being locked into a single dietary niche, these creatures appear to have been capable of exploiting multiple food sources depending on seasonal availability and environmental conditions. The front teeth of these adaptable predators were relatively simple and pointed, perfect for capturing small animals or processing soft organic material. However, the teeth toward the back of their jaws showed increased complexity, with shapes and wear patterns that indicate they were used for processing tougher materials that required more extensive mechanical breakdown. This dental specialization implies cognitive abilities that allowed these creatures to assess different food sources and employ appropriate feeding techniques for each situation. The neural control required for such flexible feeding behavior suggests brain structures that were more sophisticated than typically associated with small theropod dinosaurs. The postcranial anatomy of these versatile predators reveals equally intriguing adaptations. Their limb proportions indicate creatures that were capable of both sustained running and precise maneuvering through complex terrain. This combination of speed and agility would have been essential for animals that needed to exploit diverse ecological opportunities across varied landscapes. The hand structure of these dinosaurs shows particular specialization for grasping and manipulating objects. The claw arrangement and finger mobility suggest they could handle small prey items with considerable dexterity, possibly even using tools or engaging in complex food preparation behaviors that left no direct fossil evidence. These small theropods may represent transitional forms that provide insights into major evolutionary developments within dinosaur lineages. Their primitive characteristics combined with specialized adaptations suggest they occupied positions at crucial branching points in dinosaur evolutionary trees, making them invaluable for understanding how major groups diversified and specialized. The environmental conditions that supported such diverse feeding strategies were maintained by the complex hydrological systems that characterize Cretaceous Colorado. Multiple river channels created a network of interconnected habitats that allowed species to move between different ecological zones as conditions changed throughout the seasons. During flood periods, these waterways would overflow their banks, creating temporary wetlands that supported unique plant and animal communities. These ephemeral habitats provided opportunities for species that had evolved to exploit short-term resource abundance, adding another dimension to the overall ecosystem complexity. The sediment deposition patterns during these flood events created the perfect conditions for fossil preservation, rapidly burying organisms before decomposition could destroy their remains. This process was so efficient that we can sometimes find complete, articulated skeletons that preserve even delicate anatomical features normally lost during fossilization. The geological formations that preserve these ancient ecosystems represent millions a story of changing conditions, from periods of years of accumulated environmental history. Each layer tells of rapid deposition during major flooding events, to slower accumulation during more stable climatic periods. The mineral composition of these sedimentary layers provides additional information about the environmental conditions that existed during deposition. Chemical analysis can reveal details about ancient climate patterns, vegetation types, and even seasonal variations that influence the daily lives of these prehistoric creatures. Within these preserved environments, we find evidence of complex ecological interactions that demonstrate the sophisticated nature of Cretaceous ecosystem functioning. Predator-prey relationships, competitive interactions, and symbiotic associations all left traces in the fossil record that allow us to reconstruct the behavioral ecology of these ancient communities. The bone bed discoveries that have yielded multiple individuals of the dynamics. These mass mortality events, same species, provide particularly valuable insights into social behaviors and population, often caused by catastrophic environmental changes. Preserve snapshots of entire communities that reveal details about herd structure, age distributions, and seasonal migration patterns. The taphonomic processes that created these fossil assemblages were remarkably selective, preserving some types of organisms and behaviors while completely destroying others. Understanding these preservation biases is crucial for accurately interpreting the ecological relationships we observe in the fossil record. The chemical preservation of organic molecules within some fossils has opened new avenues for understanding dinosaur biology. Protein fragments and other biomolecules can provide direct evidence about metabolic processes, growth rates, and even reproductive physiology that was previously impossible to study in extinct species. These molecular studies have revealed surprising connections between ancient dinosaurs and modern animal groups, confirming evolutionary relationships that were previously based solely on anatomical comparisons. The biochemical evidence adds new dimensions to our understanding of how these creatures lived and functioned as biological organisms. The integration of geological, paleontological, and biochemical evidence creates a comprehensive picture of Cretaceous Colorado that extends far beyond simple species lists or anatomical descriptions. We can now understand these ancient ecosystems as dynamic, interconnected systems that functioned according to the same ecological principles that govern modern environments. The productivity levels supported by these prehistoric ecosystems appear to have exceeded anything seen in contemporary terrestrial environments. The biomass calculations based on fossil abundance suggest that Cretaceous Colorado supported animal populations of incredible density and diversity. This high productivity was made possible by the combination of favorable climate conditions, abundant water resources, and diverse plant communities that provided multiple ecological niches for herbivorous species. The energy flowing through these systems supported complex food webs with multiple trophic levels and intricate species interactions. The stability of these productive ecosystems over geological timescales demonstrates the resilience that can emerge from high diversity and complex interconnections between species. Even when individual species became extinct, the overall ecosystem structure persisted because multiple species could fill similar ecological roles. The evolutionary innovations that emerged from these highly competitive environments continue to influence vertebrate biology today. Many of the anatomical and physiological adaptations that first appeared in Cretaceous dinosaurs can be traced through evolutionary lineages to modern animal groups. The sensory capabilities developed by Cretaceous predators, for example, established templates for sophisticated neural processing that influenced the evolution of later vertebrate groups. The integration of multiple sensory modalities into coordinated hunting behaviors represents a level of neural complexity that required significant evolutionary investment. The communication systems developed by herbivorous dinosaurs, particularly the acoustic capabilities of duck-billed species, demonstrate that complex social behaviors and long-distance communication were well established in terrestrial vertebrates long before the evolution of modern mammalian or avian groups. The defensive strategies employed by armored dinosaurs influenced the evolution of protective mechanisms throughout vertebrate history. the principles of structural engineering embodied in dinosaur armor continue to inspire modern biomechanical research and technological applications. The feeding mechanisms developed by various herbivorous groups established efficient methods for processing plant material that influenced the evolution of later herbivorous mammals, represent solutions to herbivory. The dental batteries and jaw mechanics of duck-billed Dinosaurs that achieved efficiency levels comparable to modern ungulate feeding systems. The locomotory adaptations seen in different dinosaur groups explored nearly every possible variation in terrestrial movement strategies. From the cursorial specializations of swift herbivores to the massive quadrupedal stability of giant sauropods, plans that pushed the limits of terrestrial locomotion. These Cretaceous dinosaurs experimented with body locomotory innovations were driven by the intense selective pressures created by predator-prey relationships and competitive interactions within diverse ecological communities. The need for speed, maneuverability, and remarkable efficiency in energy utilization and mechanical performance durance resulted in anatomical refinements that achieve. The reproductive strategies developed by Cretaceous dinosaurs established patterns of parental investment in offspring care that influenced later vertebrate evolution. Evidence for complex nesting behaviors, parental protection of young, and extended periods of juvenile dependency shows that sophisticated reproductive strategies were well developed in dinosaur lineages. The seasonal migration patterns exhibited by some herbivorous species created large-scale ecological phenomena that influenced entire regional ecosystems. These mass movements redistributed nutrients across landscapes, created temporary concentrations of resources, and generated selective pressures that influenced the evolution of both migratory and resident species. The coevolutionary relationships between dinosaurs and contemporary plant groups drove innovations in both lineages that established patterns still observable in modern ecosystems. The defensive compounds developed by Cretaceous plants in response to herbivory pressure influenced plant chemistry evolution, while dinosaur digestive adaptations established templates for processing chemically defended vegetation. The pollination relationships that may have existed between certain dinosaur species and flowering plants represent some of the earliest examples of complex, mutually beneficial relationships between vertebrates and angiosperms. While direct evidence for these interactions is limited, the timing and anatomical features of some small dinosaurs suggest they may have played important roles in early flowering plant evolution. The impact of these ancient ecosystems on global biogeochemical cycles was substantial and far-reaching. The massive biomass supported by Cretaceous environments influenced carbon cycling, nutrient distribution, and atmospheric composition in ways that affected planetary climate patterns and ocean chemistry. The extinction event that ended the Cretaceous period terminated these remarkable ecosystems, but their influence on subsequent evolutionary developments was profound and lasting. The ecological niches vacated by dinosaurs provided opportunities for mammalian radiation that ultimately led to the diverse terrestrial ecosystems we observe today. The study of these ancient Colorado ecosystems provides crucial insights into how complex biological systems respond to environmental changes and evolutionary pressures. The patterns of innovation, adaptation, and extinction observed in the fossil record offer important perspectives on contemporary conservation challenges and ecosystem management strategies. The technological advances that have revolutionized our ability to study these ancient environments continue to reveal new aspects of Cretaceous ecosystem functioning. From advanced imaging techniques that reveal internal anatomical structures to geochemical analyses that reconstruct ancient environmental conditions, our understanding of these prehistoric worlds continues to expand and deepen. The interdisciplinary nature of modern paleontological research brings together expertise from geology, biology, chemistry, physics, and computer science to create comprehensive reconstructions of ancient ecosystems that would have been impossible just a few decades ago. This collaborative approach reveals the true complexity and sophistication of these prehistoric biological communities. The computational modeling of these ancient vocal systems has revealed acoustic capabilities that seem almost impossible for creatures that lived over 100 million years ago. The internal architecture of these cranial resonating chambers functioned as sophisticated biological instruments, capable of producing frequency ranges that extended far beyond what we initially believed possible for such massive creatures. The engineering principles behind these sound-producing mechanisms demonstrate remarkable convergent evolution with modern acoustic systems. The proportional relationships between chamber volumes, air passage dimensions, and resonating surfaces created harmonic structures that could generate complex tonal patterns with surprising efficiency and clarity. Individual species possessed unique acoustic signatures that would have been instantly recognizable across vast distances. The subtle variations in crest architecture between closely related forms resulted in distinctly different sound production capabilities, suggesting that vocal communication played a crucial role in species recognition and reproductive isolation. The social implications of these advanced communication systems were staggering in their complexity. Large herds could maintain coordinated movement patterns across territories spanning hundreds of square kilometers, with individuals responding to vocal cues that conveyed specific information about environmental conditions, food sources, and potential threats. The seasonal timing of these acoustic displays appears to have been synchronized with reproductive cycles and migration patterns. Fossilized trackways show evidence of mass gatherings that coincided with optimal breeding conditions, suggesting that vocal communication facilitated large-scale social events that were crucial for population maintenance. The energy requirements for producing these powerful vocalizations would have been substantial, indicating that acoustic communication was considered worth significant metabolic investment. The muscle systems required to generate sufficient air pressure through these complex resonating structures represent major anatomical commitments that would have influenced overall body design. The reception of these acoustic signals required equally sophisticated auditory processing capabilities. The inner ear structures of these creatures show adaptations for detecting and interpreting complex sound patterns, with neural pathways specifically adapted for processing species-specific vocal signatures. The environmental acoustics of Cretaceous Colorado would have created unique challenges and opportunities for vocal communication. The dense vegetation and varied topography of ancient floodplains would have influenced sound transmission patterns, requiring adaptive strategies for effective long-distance communication. The atmospheric composition during this period may have affected sound transmission properties compared to modern conditions. Higher humidity levels and different atmospheric pressure patterns could have influenced how acoustic signals traveled through the environment, potentially allowing for more efficient long-distance communication than would be possible today. These prehistoric soundscapes would have been incredibly rich and complex, with multiple species producing simultaneous vocalizations that created layered acoustic environments. The ability to distinguish relevant signals from background noise would have required sophisticated auditory processing capabilities that demonstrate remarkable neural complexity. The predatory species inhabiting these same environments possess their own acoustic capabilities, though these were likely adapted for entirely different purposes. Rather than long-distance communication, predator vocalizations were probably optimized for close-range coordination during hunting activities or territorial disputes. The stealth capabilities of these hunters extended to their acoustic signatures as well. Their locomotory adaptations included features that minimized sound production during movement, allowing them to approach prey without detection, despite their substantial size and weight. The sensory arms race between predators and prey created increasingly sophisticated detection and evasion capabilities on both sides. Prey species developed enhanced acoustic sensitivity that could detect the slightest sounds indicating approaching danger, while predators evolved movement patterns that minimized detectable acoustic signatures. The nocturnal activities of some species added another dimension to these acoustic ecosystems. The enlarged visual processing centers found in certain predatory species suggest they were active during low-light conditions, when acoustic cues would have been particularly important for navigation and prey detection. The circadian patterns of different species created temporal partitioning of acoustic environments, with different communities dominating soundscape production at different times of day. Dawn and dusk periods likely featured particularly intense acoustic activity as diurnal and nocturnal species overlapped in their activity patterns. The seasonal variations in acoustic activity reflected the complex life cycles and behavioral patterns of these ancient communities. Breeding seasons would have generated intense periods of vocal activity, while migration periods might have featured different types of coordination calls adapted for long-distance travel. The juvenile development of vocal capabilities in these species represents another fascinating aspect of their behavioral ecology. Young individuals would have required extended learning periods to master the complex acoustic patterns necessary for effective communication within their social groups. The cultural transmission of vocal patterns between generations suggests that these dinosaur communities possessed sophisticated learning mechanisms that allowed for the preservation and modification of acoustic traditions over time. Regional dialects may have developed within widespread species, creating additional layers of social structure and identity. The extinction of these vocal communities represents one of the most profound losses in the history of acoustic communication on Earth. The disappearance of these complex soundscapes eliminated millions of years of evolutionary refinement in biological sound production and processing capabilities. The fossilization process has preserved remarkable details about the anatomical structures involved in sound production, but the actual acoustic environment of Cretaceous Colorado remains forever lost to us. We can model and simulate these ancient voices, but we will never experience the full richness of these prehistoric soundscapes. The technological approaches used to reconstruct these vocal capabilities represent cutting-edge applications of computational fluid dynamics and acoustic modeling. By analyzing the preserved anatomical structures and applying principles of acoustic engineering, researchers can generate approximations of how these creatures might have sounded. The validation of these acoustic reconstructions relies on comparisons with modern analogs and experimental verification using physical models of the resonating structures. While we cannot be certain about the exact sounds produced, the physical principles governing acoustic production provide reliable constraints on the possible range of vocalizations. The implications of these acoustic capabilities extend beyond simple communication functions. The energy and anatomical investment required for such sophisticated sound production suggests that acoustic displays may have played important roles in sexual selection, territorial establishment, and social hierarchy maintenance. The evolutionary pressure to develop increasingly impressive vocal capabilities would have driven innovations in respiratory systems, muscular control, and neural processing that influenced multiple aspects of dinosaur physiology. The interdependence between acoustic communication and other biological functions created complex selective pressures that shaped overall organism design. The diversity of acoustic strategies employed by different species within the same ecosystems demonstrates the remarkable evolutionary plasticity of sound production mechanisms. From the deep, resonant calls of massive herbivores to the potentially high-frequency vocalizations of smaller species, the acoustic environment supported an incredible range of communication strategies. The coevolution of acoustic communication capabilities with other sensory modalities created integrated communication systems that combined vocal, visual, and chemical signaling methods. This multimodal approach to communication provided redundancy and enhanced information transmission efficiency in complex social environments. The territorial implications of acoustic communication capabilities were substantial, with vocal displays potentially establishing and maintaining boundaries across vast areas without direct physical confrontation. This would have allowed for more efficient resource utilization and reduced the energy costs associated with physical territorial defense. The group coordination benefits of acoustic communication extended to complex cooperative behaviors, including synchronized feeding activities, coordinated predator responses, and mass migration movements that required precise timing and spatial organization across large numbers of individuals. The metabolic costs of maintaining these sophisticated acoustic capabilities would have required consistent access to high-quality nutrition, potentially influencing habitat selection and feeding strategies in ways that are not immediately obvious from anatomical evidence alone. The seasonal energy budgets of these creatures would have allocated substantial resources to acoustic communication activities, particularly during breeding seasons when vocal displays reached peak intensity and complexity. The environmental factors that influenced acoustic communication effectiveness included atmospheric conditions, vegetation density, topographic features, and background noise levels from other biological and geological sources. The optimization of vocal communication for specific environmental conditions may have contributed to habitat specialization and geographic distribution patterns that influenced speciation processes and evolutionary divergence within lineages. The integration of acoustic communication with other behavioral systems created complex feedback loops that influenced social structure, mating systems, parental care patterns, and anti-predator behaviors in ways that shaped the overall ecology of these ancient communities. The loss of these acoustic communication systems during the end Cretaceous extinction event eliminated not just individual species, but entire modes of biological communication that had required millions of years to evolve and refine. The study of these ancient acoustic systems provides valuable insights into the evolution of communication and the role of vocal displays in vertebrate social evolution, with implications for understanding communication systems in modern species and predicting how they might respond to environmental changes. The recovery and analysis of these ancient acoustic systems has revealed unprecedented details about the sophisticated neural networks that controlled sound production in these prehistoric creatures. The brain structures associated with vocal control show remarkable enlargement compared to related species that lacked complex communication capabilities, indicating substantial evolutionary investment in the neural machinery required for acoustic signaling. The motor control pathways responsible for coordinating the precise muscle movements needed for sound production demonstrate levels of neural integration that rival modern songbirds. These ancient creatures possessed dedicated brain regions that could orchestrate the complex timing sequences required to produce meaningful acoustic patterns from their elaborate cranial resonating chambers. The learning mechanisms embedded within these neural systems suggest that vocal development involved extended periods of practice and refinement. Juvenile specimens show progressive changes in the size and structure of sound-producing organs, indicating that acoustic capabilities developed gradually through active use and social interaction rather than being fully functional from hatching. The memory systems required to store and recall complex vocal repertoires would have demanded significant neural resources. Evidence suggests these creatures could maintain libraries of acoustic patterns that varied according to social context, environmental conditions, and seasonal requirements, demonstrating cognitive flexibility that challenges traditional assumptions about dinosaur intelligence. The processing speed required for real-time acoustic communication in dynamic social situations implies neural efficiency that approaches the capabilities of modern vertebrates with sophisticated vocal communication systems. The rapid assessment and response patterns necessary for effective acoustic interaction required specialized neural circuits optimized for temporal precision. The integration of acoustic communication with spatial navigation systems created multifunctional neural networks that could simultaneously process location information and social signals. This dual functionality allowed these creatures to maintain group cohesion while navigating across complex landscapes, demonstrating remarkable neural efficiency in resource allocation. The environmental adaptability of these communication systems extended to the ability to modify vocal patterns based on ambient acoustic conditions. The neural flexibility required for such real-time adjustments indicates sophisticated feedback mechanisms that could assess acoustic transmission effectiveness and adjust signal parameters accordingly. The social recognition capabilities embedded within these acoustic systems allowed for individual identification across large group structures. The neural processing required to distinguish between hundreds of different vocal signatures within a single population demonstrates memory and pattern recognition abilities that exceed what we typically associate with reptilian cognition. The emotional content conveyed through acoustic signals required neural systems capable of modulating sound production parameters to express different internal states. The anatomical evidence suggests these creatures could produce acoustic patterns that conveyed urgency, contentment, aggression, or submission through subtle modifications of their vocal output. The coordination of acoustic communication with visual displays created multimodal signaling systems that required sophisticated neural integration between different sensory processing centers. The timing and synchronization of these combined signals demanded neural control systems of remarkable precision and complexity. The territorial establishment and maintenance functions of acoustic communication involved neural systems capable of spatial mapping and boundary recognition. These creatures could apparently maintain acoustic territories that corresponded to specific geographic areas, requiring cognitive abilities that integrated spatial awareness with social signaling. The seasonal modifications of acoustic behavior patterns demonstrate neural plasticity that allowed for dynamic adjustment of communication strategies based on changing biological and environmental conditions. The hormonal influences on vocal behavior required neural systems that could respond to internal chemical signals while maintaining acoustic functionality. The anti-predator applications of acoustic communication involved neural systems capable of rapid threat assessment and appropriate response generation. The split-second decisions required to produce appropriate warning calls or coordinate escape responses demanded neural processing speeds that ensured survival in dangerous environments. The cooperative hunting coordination observed in some predatory species required acoustic communication systems that could convey tactical information between multiple individuals in real time. The neural complexity required for such coordination demonstrates cognitive abilities that approach those seen in modern social carnivores. The parent-offspring communication systems involved specialized neural circuits that could recognize and respond to juvenile acoustic signals while simultaneously monitoring environmental threats. The multitasking capabilities required for effective parental care demonstrate remarkable neural efficiency in attention allocation and response prioritization. The mate recognition and courtship functions of acoustic communication required neural systems capable of assessing acoustic quality and complexity as indicators of individual fitness and genetic quality. The discrimination abilities necessary for effective mate choice demonstrate sophisticated pattern recognition capabilities that influenced reproductive success. The cultural transmission of acoustic traditions between generations involved neural mechanisms for observational learning and pattern imitation that required extended developmental periods and social interaction. The preservation of acoustic traditions across multiple generations demonstrates neural systems capable of long-term information storage and retrieval. The geographic variation in acoustic patterns suggests neural flexibility that allowed for regional adaptation of communication systems while maintaining species-wide recognition capabilities. The balance between local adaptation and species identity required neural systems that could accommodate both stability and change in acoustic patterns. The stress response modifications of acoustic behavior demonstrate neural systems that could integrate physiological state information with communication requirements. The ability to modify vocal output based on internal stress levels required neural monitoring systems that could assess multiple physiological parameters simultaneously. The group size scaling of acoustic communication systems involved neural mechanisms that could adjust signal parameters based on audience size and composition. The social awareness required for such adjustments demonstrates cognitive abilities that included sophisticated assessment of social context and appropriate response generation. The energy conservation strategies employed in acoustic communication required neural systems that could optimize signal effectiveness while minimizing metabolic costs. The efficiency calculations required for such optimization demonstrate cognitive abilities that could integrate multiple variables to achieve optimal communication outcomes. The innovation and modification of acoustic patterns throughout individual lifespans suggest neuroplasticity that allowed for continuous refinement and improvement of communication effectiveness. The creative aspects of vocal behavior demonstrate cognitive flexibility that challenges traditional assumptions about behavioral rigidity in extinct species. The integration of acoustic communication with other behavioral systems created neural networks that could coordinate multiple functions simultaneously without interference or degradation of performance. The multitasking capabilities required for such integration demonstrate neural architecture that achieved remarkable efficiency in information processing and behavioral control. The recovery of these sophisticated neural systems from the fossil record represents one of the most remarkable achievements in paleontological research. While the soft tissues of the nervous system rarely fossilize directly, the bony structures that housed and supported these neural networks preserved detailed information about their organization and capabilities. The endocranial casts that preserve the shape and size of brain structures provide direct evidence for the neural specializations required for complex acoustic communication. The enlarged regions associated with vocal control and auditory processing demonstrate the substantial evolutionary investment these creatures made in communication capabilities. From the thunderous calls of massive duck-billed giants echoing across ancient wetlands to the razor-sharp precision of sickle-clawed hunters, Colorado's Cretaceous world reveals evolutionary innovations that pushed life to extraordinary limits. These weren't primitive creatures stumbling through prehistoric wastelands, but sophisticated organisms with complex behaviors, advanced communication systems, and intricate ecological relationships that sustained thriving communities for tens of millions of years. The fossil record preserved in Colorado's formations continues to revolutionize our understanding of how life responds to environmental pressures and drives innovation through evolutionary arms races that shape the trajectory of vertebrate evolution for millions of years to come.